Lesson 1, electronic structure. So in class today, we did this kind of funny little activity where we tried to remove a magnet using a spring scale, and we had another magnet underneath a piece of cardboard that was pulling on the magnet we were trying to remove. And we wanted to see what is the relationship between the number of pieces of cardboard and how hard it is to remove that top magnet, or simply the strength of that bottom magnet. And I really love this group's look. They found that as the number of pieces of cardboard increases, the energy it took to remove that magnet, or the ionization energy, decreases. And you see this here with our chart. As the number of energy levels increases, the force here went down from nothing they could even measure here to 0.125 newtons. You see it here with 3 pieces, and now they have 4. It's going to be easier to remove that magnet. Likewise, they said if there were more protons in the nucleus, or they added that stronger magnet, it was harder to pull it away, or it had a larger ionization energy. And you can really see that here. 1 proton, 0.25 newtons, but 2 protons, there's 0.5. I want to ground you in something. When we have this relationship, we're going to be referring to something called nuclear charge as the reason. Okay. And when we have this relationship here, we're going to be referring to something called shielding. You guys thinking for a second, which one of these experiences more shielding? If you thought this one, you were correct. This magnet here is shielded by those 3 levels. And we're going to look at that in a sec. Right, so all of this relates to a really important law called Coulombs Law. Right, so Coulombs Law we can look at qualitatively and quantitatively. Coulomb's law essentially talks about what governs this attraction between oppositely charged particles. Now, they don't just have to be protons and electrons. We can talk about anything that's oppositely charged. What governs their attraction? So there's really 2 things. First of all, it's the charge itself. So larger the charge value, greater the attraction. Makes sense. If you have something, let's say like sodium plus and Cl minus, and then you have something like Ca plus 2 and O2 minus, okay, you're going to have a larger force of attraction between the calcium and the oxygen simply because you have a larger charge value, plus 2 and minus 2. Okay, well, what else? Let's look at larger. You can increase that charge. You can say the larger the distance between the charged particles, what do you think? The smaller the attraction. So the larger the value of the charge, the greater the attraction. But the larger the distance between the particles, the smaller the attraction. Okay? Makes sense. If they're farther from one another, they don't sense each other as much. You saw that by putting added levels in between those magnets in today's class. Okay? So quantitatively, we can talk about Coulomb's law in terms of an equation. So we're going to say F attraction, the force of attraction. The force you experience during this lab activity, or simply the ionization energy, is going to be equal to the product of the 2 charges, and we're calling those Q1 and Q2. So these are those actual charged particles, so plus 1 and minus 1, plus 2 and minus 2, etc. And that's going to be divided by the distance between them squared, multiplied by this constant K, but you really don't have to worry about this too much. You're not going to do any calculations with it, but it just might help people understand this quantitatively. Larger values of charges, larger the numerator, larger the force of attraction. Smaller the value of the charges, smaller the numerator, smaller the force of attraction. The larger the distance in between the particles, and this R they're really talking about it, is this distance right here. The larger the denominator, and the smaller the force of attraction. Conversely, The smaller the distance between them, if you get them closer, the smaller the denominator, and the larger the force of attraction. Either you're going to be a qualitative Coulombs Law person or you're going to be a quantitative Coulombs Law person. Don't worry about it. Okay, so let's look at an example. So we got nitrogen versus oxygen. So the first thing we want to do when we do this is identify the energy level that they're in, N, okay, and N is just the ring, so this would be N equals 1, and this would be N equals 2, and the number of protons in the nucleus for nitrogen and oxygen. Well, both of these are in the second period, or horizontal row, so they both have the same value for N, and I'll do this in red, 2. But the protons are different, so that's the atomic number. Nitrogen has 7 protons and oxygen has 8. All right. So when we look at this, it makes sense. They have the same value for the energy levels, but oxygen has more protons. Those more protons increase the nuclear pull on those electrons. Okay. So I want to write this though in the way that you should always write it for a horizontal relationship. So this is horizontal. And when we're talking about horizontal relationships, we always want to mention nuclear charge. Okay, so watch how I do it. This is how we do problems in AP. So the first thing we do is declare the answer. We get it right first. Okay. So oxygen has a higher ionization energy. I'm going to write IE for that. Okay. Now we declare the law or rule or theory that we're using to declare that. So according to Coulombs Law, CL, I want you guys to write Coulombs Law. I'm just going to write CL. According to Coulombs Law, both have electrons in N equals 2, but oxygen has a larger, here's the main point with the horizontal relationship, nuclear charge, 8 protons versus those 7 protons. Thus, oxygen's electrons experience more pull. Okay, so that's a perfect example. Horizontal reason, we've controlled for the energy levels. Oxygen has 1 more proton. It's got a higher nuclear charge, so its electrons experience more pull and have a higher ionization energy. Now let's look at a vertical one. When we're talking about vertical comparisons, it's going to be, okay, about vertical comparisons, it's going to be about this thing called shielding. That's going to be the word that I'm really looking for. But let's line it up, okay? So N and protons for nitrogen and phosphorus. Okay, well, nitrogen, here's in the second period. So nitrogen has 2 energy levels. Phosphorus is down here in the third, so it's got 1, 2, 3. Phosphorus has 3 energy levels. Now, in terms of the protons, nitrogen has 7, and phosphorus has 15. Okay, but don't get fooled by this large number of protons. When you have a difference in the energy levels, it's not going to be about nuclear charge. It's going to be about shielding. So let me show you how you write that answer here. So first, declare your answer. Well, let's look at this first. Nitrogen has less shells or less pieces of cardboard in between, so those magnets are harder to remove. So nitrogen has a larger ionization energy. Declare your answer. Now declare the law. According to Coulombs Law, nitrogen's electrons experience more pull because they are less shielded. And you think about it this way, if here's the protons and here's that electron, there's only one shield in between here. In phosphorus's case, if here's the electrons, there's two shields. So the less the shielding, the easier and the harder it is to remove that electron, because that electron is getting just completely yanked in there. You guys experienced that in class today. The more pieces of cardboard you added, the harder, the easier it was to remove that electron. Okay? So when it's a vertical situation, you always want to talk about shielding. We declare the answer, we declare the law, and then we declare that, in this case, that verb. Before it was nuclear charge, now it's shielding. Now, all these things relate to something called periodic trends or periodicity. And I'm adding this because it really relates to the way you were taught it last year. And last year, you might have learned some vocabulary. You learned ionization energy. You learned electronegativity. Perhaps electron affinity. Okay. And you were told that all of these had a trend where they got bigger as you went up and to the right. Well, I'm going to demystify this for you. Ionization energy is how hard it is to remove an electron, and essentially all of these relate to the same thing, how hard it is to remove an electron. And they all follow this trend. They increase as you go to the right, and they increase as you go up. Well, why? Why? As you go to the right, the nuclear charge increases. So according to Coulombs Law, there's a greater charge. They're in the same period, so they experience the same shielding. The greater the charge, the greater the force of attraction. As you move up, you're removing energy levels, so those electrons are less shielded and experience more nuclear charge. So yes, that's true as you go up. But why? Horizontally, it's about nuclear charge. Vertically, it's about shielding. Then there's this other one that they talked about, and that's atomic radius. Now, oftentimes you are taught that atomic radius has the opposite trend, but let's not think about it that way. If you have one atom that's bigger than the other atom, all you want to think about is the ionization energy. And then it's an inverse relationship. The larger the atomic radius, the smaller the ionization energy. The smaller the atomic radius, the larger the ionization energy. Find ionization energy first, and then it's the opposite for atomic radius. So in this situation, this one here would have the larger ionization energy. Conceptually, it makes a lot of sense. This nucleus here is yanking in on these electrons, whereas this nucleus is hardly pulling on those electrons at all. The more you yank in, the more you pull on something, the smaller you are. Okay? So when you're talking about atomic radius, find the ionization energy first. Let's do an example here. Okay. So what has a larger atomic radius, Na or Mg? Let's not even think about that. Let's think about ionization energy first. So let's do our chart. Energy levels and protons. Sodium and magnesium. Okay. Well, both of these are in the third row on the periodic table. So sodium here has 3 rings, and magnesium here has 3 rings. And I'm drawing this way for a reason. Okay. Make our little chart. Sodium is in the third, magnesium's in the third. Right away you should realize this is not about shielding. Sodium has 11 and magnesium has 12. Okay. So let's talk about ionization energy. Okay. Well, according to Coulombs Law, both have electrons in the third energy level, but magnesium has a larger nuclear charge, so it experiences more pull. So it's the opposite, so that makes magnesium smaller, and that makes sodium the answer. So let's declare it. Na is larger, or has a larger atomic radius. According to Coulombs Law, both have electrons in the third energy level, n equals 3, but Mg has a larger nuclear charge. Mg's electrons experience more pull, thus Mg is smaller. So notice we went right to kind of the anti situation, but it makes sense. We got a horizontal relationship, we have more protons, we have more pull, smaller, making sodium bigger. So when we're talking about atomic radius, go to ionization energy first. Okay. So here's a challenge for you. Who has a larger atomic radius, sodium or the ion sodium? I want you to press pause, figure it out, press play, and I'll give you the answer. So in this case, you have sodium or the sodium ion. So let's go ahead and give the energy levels and the protons. Now they're both sodium, so they both have electrons and n equals 3. And they're both sodium, so they both have the exact same atomic number.
Good afternoon, your attention please, Mr. Ferranti. Please call extension 791. Thank you.
So there's got to be something else happening here, and it turns out that it's the electrons. Okay. Whenever we're talking about ions, there's always something goofy with the electrons. So the neutral sodium here, you can think about it as Na0, has the same number of protons and electrons. And sodium plus here has one less. So when you look at this, who has a larger atomic radius? Well, the answer is sodium neutral. Well, why? They both have the same shielding, so it's got to be about nuclear charge. And actually, relatively speaking, sodium plus has a larger nuclear charge. Okay? And it's got a larger nuclear charge because its protons are only pulling on 10 electrons. So they can pull on those 10 electrons with more force, thus it's smaller. So if you wanted to do it the way we've done before, you could say sodium has a larger atomic radius. According to Coulombs Law, both have electrons in n equals 3. Sodium plus has a larger nuclear charge, or relative nuclear charge, because its 11 protons are pulling on less electrons, giving those electrons a larger nuclear pull, making it smaller, making sodium larger. So for the multiple choice question here, I want you to press pause and answer this question. Buzz your answer into the form below, the choices below. In which of the following are the chemical species correctly ordered from smallest radius to largest radius? So you probably know what I'm about to say. You should be thinking about it this way. In which of the following are the chemical species correctly ordered from largest ionization energy to smallest ionization?